to analyze the runtime behavior of an application in order to identify timing problems. So timing issues are one of the most frustrating problems in embedded applications, and developers spend a lot of time investigating them and to find what is the root cause of these timing issues. That's why I'd like to show you today how to use the debugger and trace tool Universal Debug Engine, UDE, and how we can help you to find or to identify or analyze these types of bugs. It's been a while since we have helped a customer with an application that didn't work as expected. Sometimes functions took too long to execute and other functions failed to meet deadlines. And from that support case inspired, I created this webinar. And I'd like to show you the tools that we provide in UDE to identify the biggest timing killers and to use trace for doing runtime analysis and measurements of your application. So the application that I use for the demonstration is not that application that we have seen in the customer support case, but I tried to imitate more or less the timing issue that we have seen. The application is running on an Infineon AURIX microcontroller, and it's a TC39, so the second generation of the AURIX, and it realizes a simple cooperative scheduler. The scheduler is running on Core 1, and the tasks of, it's not an operating system, but a bare metal application. But the tasks that I have implemented are executed based on fixed time slots. So we have a 10 millisecond task, we have a 50 millisecond, a 100 millisecond, and a 200 millisecond task. The correct timing behavior, that is whether each task is executed periodically according to its assigned time slot, is observed by the checker function. And if it's not the case, then an alarm is issued by the SMU, which is the safety management unit of the AURIX. So we will see the occurrence of these alarms by looking at the specific variable G_SMU alarm counter. You will see it later in the demo. And we have also a structure, a task information structure, which tells us in a error counter which task has not meet the deadline or was not executed in the expected manner. So obviously with that cooperative scheduling scheme, the overall execution time of all the tasks must not exceed the periodicity of the most frequent executed task, which is in this case 10 millisecond. So our critical path is 10 millisecond. The summarized execution time of all the 4 tasks must not exceed that time. There's also a periodic interrupt that is issued by another unit, which is the capture compare unit 6 of the AURIX, which is also handled by Core 1. And we will see what happens and what this interrupt has, which influence on the runtime behavior of our scheduler. Okay, before we go to the debugger and look into the application, a general remark on my hardware setup here. So I'm using a real target, which is a TC39B step mounted on an Infineon triboard, which can be seen here on that picture. We have connected the triboard or the AURIX to the debugger, which is running on my PC using our UDE 2 Pro universal access device, using a DAP interface, which is the typical Infineon debug interface that should be used for connecting debuggers to the device. The UDE 2 Pro is connected using USB to my PC, and we have here an adapter which is used for the AURIX or tricore based devices to connect these devices to our debugger. This is the only hardware device specific part here in this setup. The UAD can be also used for other devices as well, and also the UDE debugger running on the PC. Okay, then let's go to the debugger here. I have already loaded a workspace, and I have also flashed the application to the AURIX, and we can basically start the application. Then you see we have here some watch variables. We see here our alarm counter, which is counting up. So it indicates that we have a kind of timing problem here because the alarm is issued. And we have here the info structure for all the tasks. So each task, we have 4 of them, has a task running period. So this is the block for the task 10 millisecond. We have here for the 50 millisecond, 100 millisecond, and also the 200 millisecond task. And if you look at the arrow element here of this struct, we see that the task 10 millisecond has some problems here. We have an error counter which is counting up, and this is an indicator of a timing problem. So it seems that the task is not executed always, or not always executed in the specified scheduling scheme. So maybe some executions are missed or not, are blocked. The others looks okay, so we have no errors for the other tasks. And now we want to to find out what the real problem is. Firstly, we can do a profiling of that to get a first impression. We have different types of profiling tools. The simplest one is a profiling based on sampling of the instruction pointer of our application. For that, I select the core debugger 1, which is, or the core 1 is the core which executes the scheduler and also the tasks. And from when I selected core 1, then I can open the profiling for this core 1. This is a profiling. Stats means statistic profiling. That is based on the sampling of the instruction pointer. It took some seconds for the first results, and then we see after a while that we get a diagram with some values here. The values means percentage of CPU time. So we have here our tasks. We see, okay, we have a small portion of the CPU time spent in the tasks, except of the 50 millisecond task, which has a greater impact on the CPU time. And then we have a very large portion of CPU time, which is used by the core 1 main function, which is basically the idle task here. So it seems that we have a relatively large impact on the CPU time by task 50 millisecond, and this may here it could lay in the problem that we have seen with the 10 millisecond task. Okay, but from that diagram, it's hard to find out what is the root cause for the problem that we have seen. That's why we want to use another tool, which is based on trace. And for that, I like to introduce trace a little bit. So trace is a technology or a method, or basically also a hardware feature that has become more and more important in the recent years for debugging and especially for analyzing the runtime behavior of an application. It is a hardware feature and can be found on within many microcontrollers and system on chip nowadays. Sometimes a trace comes with a small feature set. Sometimes we have a very powerful trace implementation, and you have to use dedicated development devices to have all the powerful features for trace available. In general, trace is very useful when you need a deep insight into the runtime behavior of your application. You can observe the execution of your program code. That includes, of course, the functions, and if there's an operating system in place, also the tasks of your operating system. Or you can look at data transfers or into the memory, or if you have a very powerful trace system available also onto the system buses. While the system is being traced, the data are recorded as trace messages, and these trace messages are output into a trace stream. This trace stream can either be stored in an on-chip trace memory, then we call it on-chip trace, if the device has one, or you can directly transfer the trace stream to the debug probe or the trace probe via a trace interface, then we call it off-chip trace. The key feature of trace is that you can do this observation of, for example, the program execution completely non-intrusive. That means without any influence on the runtime behavior of your application. You can debug without interrupting the device. So you can typically run your target at full speed, and you can measure timings very accurately with trace. And so trace is very interesting if you want to analyze timing of your application or to identify bugs caused by timing issues. For the AURIX, which is our target device today, we have a very powerful trace system, which is called MCDS. The MCDS is part of the so-called emulation extension of the AURIX. It's important because we differentiate between so-called emulation devices and production devices, and only the emulation devices can be or provide the trace functionality. But you can exchange these chips because they are pin compatible. The MCDS contains trace observers, or so-called observation blocks, and we have multiplexers here for selecting trace sources. So the trace sources can be cores, buses, or peripherals, and the trace observers or observation blocks, for the cores are capturing trace information of the executed instructions and functions and so on. Data transfers can also be observed by so-called bus observation blocks. Each of these observation blocks provide trigger and filter capabilities that helps you to reduce the amount of the generated trace data. We have then also a cross-triggering unit that allows you to distribute events between the observers, and together with these triggers and filters you can realize very specific trace tasks. For example, you can enable the program trace on one core if, for example, an interrupt service routine on the other core is entered. The emulation device provides also a dedicated on-chip trace memory for saving the captured trace information. The size of the memory is up to 2 megabytes. The actual size which is available depends on the device. So if you record the trace information into that on-chip trace memory, you can transfer the trace via DAP, which is the debug interface from the on-chip trace memory into the tool. And then for some emulation devices, we have also a trace interface available, which is based on the Aurora protocol, which is called serial trace or our gigabit trace interface AGBT, which is a serial interface, and that allows you to trace to transfer the trace data off chip into the debug probes or on the trace probes. For that we have the UDE2 Next with a trace memory built in, and also the UDE3 Plus, which has also trace memory built in. I use the UDE2 Pro, which has no trace memory at all, so we rely on the on-chip trace memory. Okay, what's the reason for using trace? So we have basically two use cases, which is trace-based debugging and trace-based measurement or runtime analysis. So trace-based debugging is useful if you want to try to find bugs that are caused, for example, by parallel execution or caused by timing problems. In general, you can use trace-based debugging whenever the debugger access would possibly hide the bugs you want to analyze. For example, you hit a breakpoint, everything is halted, and the bug is gone. Trace-based debugging is useful if you want to avoid any influence of the on the runtime behavior by the debugger. Another use case is you can use trace-based debugging whenever you need more than a snapshot of the target state. For example, if you are on a breakpoint, if you want to look basically back in time. Trace-based measurement covers a lot of useful things to analyze the runtime behavior. So examples are profiling, call graph analysis, visualization of the program execution, and so on. And we want to look in a minute to these three kinds of tools. Performance analysis is also possible with trace, and also code coverage. Code coverage is useful if you want to do automatic tests and you want to prove the quality of your tests without any code instrumentation and other influences on the runtime behavior. So let's go back to UDE and look how to use the trace for analyzing our problem here. First of all, if you want to use trace, we have to configure the trace system accordingly to the use case. In our specific case, we want to trace, or we want to observe the task execution on core 1. Best practice would be to start the trace recording at a specific point in time and record everything after this point in time, or you can alternatively trace everything between 2 points in time. For example, to trace only a single period of the scheduling scheme here. In our case, I'd like to use the first option, so starting the trace at a certain point in time and then trace as long as we have enough trace memory available. So I close this window here and open the trace configuration. This is the tool that allows us very simple or easy set up a trace for our use case here. On the left side, we have a library of configuration blocks. And here on this empty panel, we can use these or drag and drop these blocks to configure a trace task. It's quite simple. You can use your mouse, or you can double click here to drag and drop these configuration blocks. The first block that I added to the configuration panel is an initialization block, which is always needed. Here you specify the amount of trace memory you want to use in the trace. For your trace task, I select all the available memory, 2 megabyte for this device, what I have on my desk. Then we have a trigger setting. The trigger means, or a trigger is a point in the trace memory, which is issued by a certain event. A pre-trigger means that the trigger event starts the trace, so everything after the trigger is recorded. Then we have a post-trigger, that is the opposite one. Everything before the trigger event occurs is recorded. And then we have a mid-trigger, which allows us to trace everything around a trigger condition. We are using pre-trigger because we want to start our trace at a certain, when we enter a function, for example. And then we select the core, which is core 1. This is a limitation, or we have limited here to only a single core trace, because this is the library for basic tasks. We have also a library which is called advanced, which allows you also to define in a very flexible way also more complex tasks and also multicore traces. But right now we are concentrated only on core 1. That's why I can use the compact library here. But the trace system of the AURIX is of course able to do a multi-core trace. Okay, then we need to configure the trigger condition. This is the second block here, which allows us to specify a code address, or we can select from the function list we are looking for core 1 worker. This is the function. When we enter this function, then the trace should be started. Then we have the trace method. There are 3 possibilities. Branches only is the default, which traces every branch, interrupt, calls, returns, everything that leaves the sequential execution of the instructions of the application or your function. The sequential executed instructions can be reconstructed by the tool itself. So it makes no sense to record all the executed instructions. So a branch trace should be enough. Then we have also all instructions which consumes a lot of trace memory because you can record everything. That means all the executed instructions, also the instructions that not changing the sequential program flow. And then we have a nice feature in the AURIX, which is the compact function trace, which only traces calls and returns. And this saves a lot of trace memory, and I decided to use this in our example. But there is a big but and a big limitation of that. It is only working properly if you have a non-optimized code, because the analyzing or the trace system expects that for each call a return exists that goes back to the caller. But there are some optimizations that are changing this. And so it is not ensured that if you use optimization, that the trace analyzing can reconstruct the correct program flow. But in our case, I have a debug built here without optimization, so I can use the compact function trace. And then we need, of course, some information about the timing. So I enable this option and create so-called tick messages. And then I add another configuration block, which helps us to detect interrupts within the execution, and that helps. That is helpful for the analyzing functions within the UDE. Okay, that's all. Now I can start the trace. I open the trace window, and then I can, for example, use the context menu, or I can use the toolbar buttons here to start the trace recording. It took a while to configure the device, and then we have our trace here. It's automatically stopped because we have a pre-trigger set up, and the trace is stopped automatically once the trace memory is full. And you see here all the recorded calls and returns, and somewhere also some information about the interrupts here. But this view is not very useful for analyzing our problem here. That's why I opened another one. This is the core graph. And the core graph is core specific. So I select core 1 and start the analysis. And it took a few seconds for the analysis to be finished. And then we have different views here, which is the first view is a core graph, which shows us the core relations of our functions. And then we have also some tables here. And I like to go back to the slides and introduce the core graph analysis a little more in detail. So I mentioned before, the core graph shows us the relationship between the executed functions. So it shows us which functions were called from a specific function, or vice versa, from which functions a specific function was called from. The core graph can be calculated from trace only, but yeah, we need these runtime information. And in the ideal case, it would be nice to have a complete trace of the overall execution time of the interested part of your application. With the limited trace memory in real world, we have only a limited amount of trace data available, so you have to be a little bit careful when you set up your trace to get a good core graph analysis. You have not only the core graph, but you get also some statistic information. You will see it later. We have core counts. We have information about the execution time. We get detailed profiling information and so on. We have two representations of a core graph. We have a static one and a dynamic one. So the static core graph, in the static core graph, all the calls of a function are accumulated, regardless of who was the caller. And in the dynamic core graph, we also considering the caller, so you can so you have a difference in the number of calls. So if you look at this example here, we have a function A that is calling function C 10 times, and we have a function B which is calling function C 2 times. Overall, C is called 12 times. In the static core graph, we see always C is called 12 times, and in the dynamic core graph, we differentiate between C is called from A or C is called from B, and we see the number of calls of 10 for function C was called by A directly, and a number of 2, which is the case if B is calling C. In addition to that, in the dynamic core graph, we can also switch in UDE in timeline mode. This option, in this option, every single call is represented as a separate node in the dynamic core graph. And this way we get the maximum expanded tree, and we will see that helps us to find some hotspots or some special nodes or special calls that are very interesting to us if we want to find some timing bottlenecks. Okay, then let's go back to UDE. We have here our static function graph, which some timing information here. And if we look at the maximum time and sort it by the maximum execution time, then we see that we have a larger portion of our CPU time spent in the core main and the core 1 worker functions, which are the idle tasks. But then we see that the 50 millisecond task has a maximum execution time of 21.33 milliseconds. And we remember that we had a maximum allowed execution time of all the task functions of 10 milliseconds. So this is far too long in the execution time in order to have a good scheduling. So we have some executions with 4.6 milliseconds, average 6.84. This is okay, but this is not okay. So 21.33 is not okay for our scheduling. So this task will definitely block some of the other tasks. In our case, we have seen it for the 10 millisecond task here. Okay, and now we want to find the reason for that. Now I switch to the timeline mode. I have to restart the analysis again, and then we can look at the dynamic functions. And here we have a list of all the executions of our functions here in the trace. Every single execution can be found here. And if we sort them by the execution time, then we find again the executions of our idle task functions here. And then we have 6 executions of our 50 millisecond tasks, which took 21.33 seconds. And these are the problematic ones. Everything below seems to be okay. We have also a lot of 50 millisecond functions, which has an execution time of 4.67 milliseconds, but we are looking for the bad ones. And we can now go to the graph. And we see here it's not seen very good because we have here a bar which indicates us this is the node in the graph. And we see here we have a execution time of 21.33 milliseconds. And we can now look in the leaves of this node here, and we see we have called a check-in time function, which is rather small in terms of the execution time. And then we have functions that seems to be an interrupt by name, which is 16.67 milliseconds, and that is far too long for our scheduling scheme and the critical path of a maximum 10 milliseconds here. And it seems that the task 50 milliseconds was interrupted by this interrupt service routine, which is the interrupt service routine of the CCU6 timer here. And we have here the service routine, and this service routine calls a delay function, which consumes a lot of CPU time. We can also double click and go to the code and look here into our functions here. And we see this is a bit generic and a bit a trick to create this behavior here. But we see, okay, we should do something with this interrupt handler here. Maybe we can move it to another core so that the scheduling and the tasks are not interrupted anymore by this interrupt service routine. So with the core graph, we have now analyzed our problem here. So we have seen there is a problem with the interrupt handler here. We have a solution for that, moving the interrupt handler to another core. But you can also visualize this behavior in a nice way for this timeline mode representation. We have a nicer view, which is called execution sequence chart. And if we start the analysis of the execution sequence chart, and wait some seconds, then we see this diagram here, which shows us over time the execution of all the functions here. If we zoom a little bit in, for example, here in this case, at this point in time, then we see the problematic that we have seen or analyzed. Our 10 millisecond task was not executed in time. The 50 millisecond task, which was started right here, was also interrupted in this period by the delay function that was called by the timer interrupt here. If we zoom a little bit in, then we see here the point in time where the interrupt handler is started and then calls the delay function. With that view or with that window, you get a good impression of the execution of your task, and it's very helpful if you analyze, for example, such kind of periodic task or periodic function execution. In this example here, I have a bare metal application without any operating system. I have implemented the task scheduler manually by hand. But if you have an operating system in place, for example, in safe autos, FreeRTOS, or even an AUTOSAR application, then you can add also the information about the task executions here into this diagram. With that, I'd like to end this webinar.